but the most important concept in NLP is attention. This is used in multiple locations for translations and summary and stuff. Let me take an example in the context of summarization. Let's say you, or even translation too, let's take an example of translation. So you have an English sentence and then you actually have to translate into a French language. Let's say the input was 10 words long in English, and then the output is, let's say, 7 words long in French. And the 6th word, when you're making a translation, creating the French word, 6th word in the translation, the model has to understand which word in the input should I be paying attention to. Because just because it's the 6th word in the translation does not mean that you should only look at the 6th word at the input. It could be the 2nd word, or 1st and 2nd word, or maybe 2nd and 5th word. We don't know. For the model to become intelligent enough, it's like a human being. Like when you are translating, you want to, after 3 or 4 words, you want to go back and read the sentence again. And this time you will, even though you read the entire sentence, but you pay more attention to a few words. So attention, which is same as when you're doing a translation or any other NLP activity, the model will go back and look at the hidden states of encoder, but it wants to pick only the hidden states of some inputs, or maybe x1 and x3, or x2 and x3, whatever. It identifies, based on the training it gets, it knows what words to pay attention to. So attention as a concept will allow the decoder to go back and pay attention to those specific and relevant words of the input. Whereas in this model, it is getting the entire hidden state of the encoder. So it has access to all the information in one go, and the model does not know, okay, which word should I pay more attention to when I'm making my 2nd word translation? Should I pay attention to this or this or this? Whereas in this approach, it's just giving H3, which has all the information together. It says, no, I don't want all the information. Tell me more about 2nd word. That's what attention is. And mathematically, well, that's the conceptual explanation of attention. But in this, that is a complicated picture. Let me go to the next picture and come back to this again. Yeah. So you have the encoder, or the input information coming in. Attention, you devise a mathematical equation which takes into consideration all the hidden states, and based on and you train the model in such a way that at any timestamp t, it looks at the hidden states and picks which hidden state should be looked at more carefully. So there is a factor called alpha, a multiplication factor or an average factor. The average factor will give a number for h1 as 0. That means don't look at this word, and also may give a alpha as a score for hn as 0. That means don't look at h1, but it may give a factor of 0.7 for the word h2. So say look at the 2nd input and hence the 2nd hidden state, because the average alpha factor for that number is high. And if it's a fraction of 0.5 and 0.3 or 0.2, that means it's actually asking you to look at 3 different words, input words, and not one word. So going back to this mathematical equation, so it's doing alpha here, it's multiplying the hidden states of all the inputs, and when you're making yt as a prediction, it looks at what the score for alpha can be, and based on what alpha number is for h1, if it's 0, then it doesn't look in here. If the alpha factor is, let's say, 0.7, it gives 70% weightage here, and the rest of the 30% weightage here maybe, and the rest of the alpha numbers will be 0, so don't pay attention to any of those things. That's called attention. Yes, sir.
Is that a 2-layer or 3-layer ONN?
Right here, this is actually a 2-layer where you have a bidirectional LSTM. Actually, I didn't want to explain the concept because I think we didn't talk about it. But instead of having one LSTM, here what the researchers have done in this paper is they actually have 2 LSTMs. So one LSTM, they are giving inputs in the correct sequence, and the second LSTM, they are giving inputs in the reverse sequence. So let's say the cat sat on the mat, then another LSTM is getting mat the on sat cat. The logic in that is, when you're giving the first word the, sometimes and the next word is the cat, so by the time you look into the word cat, it knows what the previous word was. Sometimes it wants to know what the next word is too. And to know the next word is, sometimes if you give the sequence in a reverse order, you actually can know what the previous word was, or the next word is going to be. So bidirectional LSTM as a concept is used where at any timestamp, you not only know the past, you will now know the future too, because you have given the inputs in a reverse sequence.
Sure. So, yeah, I mean, it's kind of like a four-man parse tree. We don't really know the parse tree. But why is it better to use a tangent activation function instead of linear?
Why is it better than?
Yeah, the activation function in your RNN is tangent. It's not linear. If you're trying to learn that multiple words in that sentence might correspond to...
Where's the tangent?
On the next one.
Okay.
Tangent.
Tangent you're talking about?
Yes.
Yeah.
Why
So
use tangent instead of...
there are multiple nonlinears. Tangent is one of the nonlinears used. I think ReLU is another nonlinear being used. In this case, the researchers have used tangent in this case, and they have I don't know the exact explanation why this makes sense. But by default, I have seen any of the nonlinears used. Most frequently used ones are ReLU and tangent.
I'm trying to say why does it feel more right to use nonlinear than linear? You're trying to learn that multiple words in the input.
Okay. When you do a nonlinear, the entire concept of nonlinear is when the model is outputting numbers, you want to squash it down to the number between a range. Let's say 0 and 1, or -1 to 1.
So kind of like regularization.
Yes. Yeah, it's a regularization. Yeah. Right.
Just to check my understanding, so the attention layer, one of the things that implementation helps with is if you're doing a translation and the word order changes, then for what you're outputting, if the third word there actually depends on the fourth and fifth words of the input.
Yeah.
And that's what the attention helps with.
Exactly. That's, or even summarization. Let's say if you have 10 sentences has to be made into one single sentence, then which of these 10 sentence words need to be paid attention to also helps in the attention process.
Okay.
And it also goes back to your question answering. Let's say if you have a question and the model narrows it down to a passage, it has to know out of these 100 words, which words I need to pay attention to find the answer for my question. So any of the NLP model, when you have a bunch of text that's coming in, instead of having the entire text, I think when I started explaining LSTMs or RNN, I said, okay, if you have 100 words, give all the 100 words and it becomes intelligent enough of all the 100 words, which is fine, but if you want to fine-tune the activity of the LSTM, while it's outputting some things, it may want to go back and check, what's the 45th word? So that attention will help going back. So having the hidden state of the entire input text also helps. Plus on top, if you have an attention layer, it goes and looks at specific words, a specific collection of words to fine-tune the output, whether it's translation, question answering, summarization, whatever it is. So it helps. So attention, the hidden state plus attention layer together will enhance the accuracy.
Thinking like an example would be in English, like you got out of the car, and in German, and Keras after Wagen ausgestiegen, because there's a compound word at the end of the sentence, and it corresponds to got out.
Yeah, I don't know the German, but yes, that's the conceptually yes. It goes back and looks at the gender, the temporal aspect, compound words, all of those things. It goes back. Yeah.
So the alpha is the weight for the attention, right?
Mm-hmm.
And so the all alpha has to sum up to 1.
1, yes, absolutely, yeah. Attention again, another layer. I think it goes back to a different paper again, where they proposed different types of attention, where they want to enhance the accuracy because of attention. In this case, you have the inputs, there's something called skip level inputs. So when you have multiple layers of LSTMs doing an encoding activity, normally the stacking of LSTMs, you have the input going into the first level LSTM, and the output of that LSTM goes to the second level, and the output of that goes to the third level LSTM. That's how you actually normally stack LSTMs. The reason why you stack LSTMs is it actually captures information better even. It's actually a lot more precise. So people actually do stacking. But the problem is there's a limitation on the stacking too. The more stacking it is, it's computationally expensive. You've got to have massive GPUs and CPUs and more memory, more time, all of that stuff. So there's a limit of that. So without stacking too much, you can still have it stacked, but to increase the accuracy, you can also have a skip level inputs where the output is not only goes to the immediate layer above, but it also goes to the one layer above. So the second layer gets not only the inputs from the previous layer, it gets the inputs from the one layer before that also, so that the information that may get missed out from first to the second layer will not happen now, because I think that this layer actually has access to the information from the previous layer. So that's the skip level, which is more of a fine tuning of your attention. So attention is have a average alpha numbers for attention, and then that is helps you to pay attention to which words, but you can also increase the overall accuracy by having skip level. In this paper, people have proved, they've proved a few things. I did not introduce the term GRU, gated recurrent units, or another variations of RNNs. So first were RNNs, and then came LSTMs and GRUs. LSTMs have 4 layers. I think I explained to you 4 different layers, 3 gates and another layer, 4 layers. GRE has only, I think, 2 layers. People felt GRE is going to be computationally simpler, but the eventual results prove that LSTMs are far better than GRE. So if you are trying to define an NLP model, and some experiments in NLP, and if you want to use, if you are confused between LSTM and GRU, by default start using LSTMs. Also, even though logic explains that the deeper the network is, if you have multiple stacks of LSTMs, may sound better, but sometimes for the, at least the encoder part, it's better to have a shallow networks, not 2 deep networks. This is, yeah, explanation of, now, so let me, I'm trying to see how much I can cover. I explained this conceptually, and it sounds so complicated. But when it comes to implementation, remember I explained about just a sequence-to-sequence model? It's just a one line. Model is equal to simple sequence-to-sequence, and then you identify the various dimensions and inputs, and that's it, you're done. You are defined a sequence-to-sequence model, and I showed you a picture with a peak, where you want to constantly go back and check the hidden state of the encoder at every time. All that, it's exactly the same, you just have to say peak is equal to true. So if you pick Keras as your framework, of course there are similar models to even TensorFlow and Piano, and I don't have working experience in Kafka and other places, but they also may be equally good. But the programming aspect of these solutions are extremely simple. Like peak, all that you have to do is just peak is equal to true. And if you want to implement an attention, which seems to be so complicated, identifying the alpha numbers and what fraction to take and all of this stuff, it can be just that you pick the attention model, attention sequence, and that's it, you're done. So when you want to do an NLP, I know the organizers at this conference, I think, wanted me to talk about hands-on other stuff. The hands-on part is the simpler thing. The implementation is easier. Of course, it's not trivial. You got to do a little bit of study there too. But conceptually understanding is a lot more important. If you don't understand how attention works, if you don't understand how sequence work, how a hidden state works, doesn't matter whether the library is available, because sometimes you just don't know which one to call and what function to call. Now let's talk about word to vec. This is an extremely important concept. We talked about one-hot vectors, and we talked about co-occurrence vectors. I think in the last 1 year, 1.5 years, Google came out with a new method called word-to-vec, and there's another, no, Google came out with a method called GLOVE, Global Vectors, G-L-O-V-E. Word-to-vec, I forgot who actually invented it. Word-to-vec is another approach, and I have used word-to-vec. I've not used GLOVE as extensively, just once I think I used, but I've used extensively word-to-vec, and I've used one-hot vectors. I've found one-hot vectors sometimes very, very effective, and I've found in some other problem statements word-to-vec also very effective. So if you are trying to use NLP models, and if you wanted to use what type of vectors you want to create, you can go for one-hot vectors. Again, creating one-hot vectors is very simple. It's just a one-line program. You can just call and then it creates the vectors out of the vocab. And word-to-vec is also one line, just a simple one line based on the vocab you're giving. It just gives you a vector line. But conceptually, the word-to-vec is created, that is creating vectors out of words, is done in two different ways. One is continuous bag of words, and the second approach is skipgram. In continuous bag of words, the approach taken to create a vector is you are predicting what the next word is based on the context, that is based on the previous and the following words. And it can be one previous and one following, or two previous, two following. So it can be whatever it is, and that's called a window. If the window size is 4 or 5, then you have 2 and 2 of each side. So depending upon how large the window you want to pick. Of course, if you're creating a word-to-vec using a large window, computational becomes expensive. But people have found a word, the meaning of a word is influenced by not more than 7 words on either way. In normal English language, people have found a word is the meaning of a word is influenced by not more than 7 words before or after. You can say, okay, maybe the possibility of a word getting influenced by a word which is 1,000 words ahead or follow is quite rare. That's what. So the windows, you can pick a window of 2 or 3 or 4, depending on what you want. But typically, I think people take 2 as a window where they actually have 2 words before and 2 words later. And using the context to predict the next word is the approach for continuous bag of words. In skipgram, using the current word, you predict what the next words are. The previous words are the following words. Those are the expressions. But I don't want to get into too much of explanation because the implementation of this word-to-vec is very, very simple. Just had a one-line code and calls. Okay.
Brief question. What do you do at the sentence boundaries? For the word 1 or 2 at the beginning or end.
So
is there some like null or?
So typically, I think they put the end of sentence notations at the end. So if you have a 2 window, you take period also as a word, and if the window is longer than that, you actually start putting unks, and hence UNK unks. But then having a larger window also does not make sense towards the end of the end of the sentence words. But on a large vocab, that averages out. So even if you have a window of 2 and you have a last word, what would be the next 2 words? You'll actually put a period and an unk next to it, and then still try to make sense out of it, and the effectiveness of word-to-vec is still high. Okay, so let's run the word-to-vec.
Is this applying a pre-trained Google word-to-vec, or is this training word-to-vec?
This is actually training the actual word-to-vec, the code, which where is that? So this is available in TensorFlow. Let me see if I can show you the whole thing. This is from TensorFlow, the actual representation. So when you use the word-to-vec in your actual existing program, this gets called. So you have the TensorFlow in the background running, and the whole file gets executed. I just want to show what the file is and how it works. But when you use a word to vec, when you're creating a vector out of a word, all that you have to do is just give the word and then say word to vec, and it actually converts that into vector and gives you a vector. But in the background, what it's doing is actually it's picking up. So it actually has, it's based on the data set. So it actually downloads, I don't know, this file, whatever they're picking up. So we'll download the file if it's not downloaded already, read the file, identifies what the size of the vocabulary is, then build a data set out of it, and then it make batches out of the vocab and then runs the batches.
Is there stop word removal or stemming or?
Let's see. It has unc words. I think it puts in uncs. Because typically I think they call multiple files from each file. So I don't know if one of these functions actually is calling lemming and stemming. Yeah, I don't know the answer for that question. But if I go look into the code, I think I'll figure out. But I think from this file, I'm looking at if it's making any API call for lemming and stemming, but I'm not seeing it. So skip window, it talks about how many words to consider left and right, and number of skips is the number of times to reuse an input to generate a label. Embedding size is the size of the LSTM, the dimensions of the LSTM, and then batch set how many inputs per run. The best part is it actually creates, I think it creates tsnif file too, image too. Let me see, that's what it actually is doing.
Just
Yeah, it does it.
With most common words.
Yeah. So I'm actually running it now. It takes, so it's down. I already run it once, so it's not downloading the file anymore. It's actually, otherwise it downloads the file. Text8.zip. I think that's the file. I think it's referring to the data set. So data set data size around 1.17 million words. The most common words are uncs. There are around 500,000 uncs and almost 1.1 million these. I think it's taking off those words. I think stoppers. I think it's taking off. But again, so it's what it's computing. It's actually computing the nearest words for some random things, like nearest to the word it's. These are the words it finds, and it does that. It's doing multiple epochs. So if you look into the code here, I think it's supposed to run 100,000 times, I think. So you have 25,000 steps done. If you have on your machine, if you're running it, the best part is, I think I already have it here in the file. It actually creates a file called tsnif.png. This is actually a file on the same data set which I've ran yesterday, so I'm just showing it to you. Even though the file is running right now, it'll take, it's not more than a minute, I think. It's already 44,000. 100,000, I think it'll be done another minute. So I think it's here, yeah. So this is the two-dimensional image of the words converted into a vector. So when you create a word into a vector, it's a number in a space, not 2 dimensions, it could be hundreds of dimensions. Now, humanly, it's not possible to visualize such a word embedding. So let's say you actually have words in the space hanging, and it's hundreds of dimensions. To understand that, you actually have a tsnif image which tries to consolidate into a 2-dimension image. And these are the, I don't know that I can show. look at, so based on the data set given, the word and, because, use, they appear closer to each other. So they are almost kind of similar. They appear close enough to each other, and so this is the similarity and quotient similarity, etc. These are some of the mathematical terms being used. These, so in other words, is the word law and the word, let's say, water, don't appear close enough. They don't appear commonly together. They're not in the same sentence. And that information gets converted into vector also when you're making a vector out of the word. So this is the two-dimensional image of the words converted into vector, which will show which vectors are closer, which vectors are too far away, which also shows which words seem to be occurring closer, seem to be occurring so far apart. So, yeah, let me...
What does the color mean?
Color, yeah, it's a good point. Actually, I need to read the file, but I think it's various classes. I don't know the answer, sorry. Yeah. But typically the TSNE image I think is shown, is trying to boil down a multi-dimensional image into two-dimensional just to visualize. If you run the same file one more time and then do another two-dimensional, it may pick some other dimensions and hence the image may look different, but the words that appear closer to each other than the words that don't appear to close enough to each other will be relatively same in any image you're going to create out of it. So let's go back to my file. I think it's done. Yeah, it's done now. So if I go back and look at, see, it's created just now. It's 12:01. Yeah. So I can open this. Let me first close this. So it's so the word important and open seem to be occurring close enough frequently for the model to figure out the vectors in such a way that when you represent the vectors in a two-dimensional image, you can see the words also occurring together. That's the beauty of word to vector. Similarly, I think GLOVE also, global vectors method approach by Google also it has a great capability. So using word to vec to convert word to vectors actually is more effective because it actually captures lot more information of a word, co-occurrences, the sentences, where it occurs, how frequently it occurs. There's so much information it captures into a vector, and that's a lot more useful when you're using those vectors to compute your NLP problems. Okay, let's get back to our presentation. I wanted to show you a Keras model, but which is not necessarily NLP problem, but I just wanted to show you how simple it is to define a model using Keras framework. If you don't have familiarity with any framework and if you want to start using, I would prefer to use a TensorFlow because it's actually a lot more flexibility and a lot more deeper. They can do a lot more things, but Keras actually works on top of TensorFlow, so you can use TensorFlow as a backend for Keras, and then it's very, very simple to write a model. In 3-4 lines you can write, and I wanted to show this example where this is not an NLP example, this is a machine learning example of trying to predict the Pima Indian women, the probability of they getting diabetes in the next 5 years based on this data. Just based on these 8 different items. The number of times pregnant, plasma glucose concentration, this diastolic blood pressure, the skin fold thickness, 2-hour serum, BMI, diabetes, and age. Just those 8 factors, I think they have a data for I don't know how many patients they actually had. And a class variable that is prediction, yes or no, whether they got diabetes or not. And it runs beautifully, and the model, I think it just takes, overall, the entire neural network to define this problem statement is, I think, 10 lines. You will be amazed. "23 lines. Entire model is only 23 lines to run a deep model using Keras to identify, to classify this data, PIMA patients, to identify who will get diabetes in the next 5 years and who will not get diabetes. 23 lines. That's what I mentioned earlier too. To define an NLP model in using deep networks is very, very easy based on the frameworks given. But conceptually, I think people need to understand. I think you've got to understand how attention works, how sequence to sequence works, how the dimensionality of your model works, what is fully connected versus sparsely connected models. You've got to understand that. For example, here is dense. You're actually, model add is, you're just creating a first layer. Another model add is creating a second layer of your neural network and a third layer of your neural network. And for each network, you're defining whether it's a fully connected network or not. So dense called densely connected is fully connected network. And what will be the dimensionality of that? How many neurons in that layer? And the input dimensions and activation. That's it. This is just the one line creates one layer of your network, and you have 3 layers you're creating, and you're defining the model, then you're asking it to compile, and the compilation is how to compute the loss and how to optimize the loss, that is reduce the loss. So you have a loss parameter and you have an optimizer parameter here. Then after that, all that you're doing is, okay, now run it by giving the data. So I've designed what the model is. I told how the model should compute the loss, and then when the model is defined completely, you fit the model, that is, you run the model with the data given. X and Y is the data, and you define what the data X and Y is here. And that's it. After that, you do an evaluation which actually computes your accuracy rates. The whole model will run, I think, in less than 2 or 3 minutes. I can run it for you guys.
That's an in-sample evaluation.
Sorry?
In-sample evaluation as opposed to on test data.
This is, yeah. It's an evaluation based on the test data. The accuracy prediction is based on the test data. So it actually takes, I think, 10% or 20% I think data aside for the testing purposes, and it computes the accuracy based on that for the 20% of the data. Yeah.
Oh, what's this done with other to compare?
The framework, this is Keras framework, and you can also use TensorFlow. There are a lot of other frameworks available too. Yeah.
Oh,
Yeah.
What it means underneath, I mean, it's just deep neural network.
This is a neural network. The way of defining is neural network. I think this is running on top of TensorFlow. So when you say model add dense 12 input dimensions equal to 8, it knows what API calls to make into TensorFlow to create a model. And then so when you're designing the model in these 3 lines, then you're telling the model how to compile or how to compute the cost and the loss and the optimization. And after that, you're just giving a command, okay, run. It uses the TensorFlow framework and picks up the right API calls and passes the data to those APIs, and then runs the data for you and gives the eventual accuracy rates. And here the accuracy you're trying to predict is, the metrics you're predicting is accuracy. Where does it say accuracy? So let me run it for you. It will show.
So how is it connected to NN? So I think I just got lost in the connections.
This example, I think I mentioned to you all, this is not an NLP example. No,
Okay, you're
this is
just
not.
showing it for just
I'm only
the
showing this to show how simple it is to design a deep neural network using Keras. Because see, so what I'm trying to do in the whole today's session is I'm introducing various topics of NLP, but I'm also showing some implementation details about how easy it is to do the POS tagging, the NER, and all of the other tagging. But if you want to really run a deep neural network on this, I can't run the entire deep neural network in the class today because it's going to take multiple hours to do. But I just want to show an example of, if you want to do Keras, in 23 lines, you can define a model for this data set. You can do maybe 50 lines maximum or 100 lines maximum for any other NLP solution you can work on using Keras. But of course, the flexibility is lost because it's a little more an abstract level code. But if you really want to do further customization to improve the accuracy, final 2 points extra, and also make it faster, you can go to TensorFlow and other stuff. But I just want to show this example as.
Keras is that framework, but makes calls to TensorFlow
Yeah.
API.
So Keras uses TensorFlow as backend, yes.
Yeah, but you're running it on your.
TensorFlow and Keras both are running on my machine, yes, on this laptop. Yeah. So if I want to talk about translation, how to do the translation, so you have to start with the sequence, and then of course you use the encoder-decoder, and then you add on top attention model on that. Then you also do a language model. So let me see. So this is a language model. What is the meaning of a language model? A language model helps you in so many different ways, but let me explain. Language model is a deep neural network where you are training the model to understand how sentences are constructed. And eventually, when you give an incomplete sentence, a language model will predict what would be the next word and the word after one and the word after. So it is like a human being which has read, let's say if it's based on Wikipedia, if it's read all the Wikipedia articles, and now if you give it a new sentence, it can predict what the next word is and the next word is. And this is actually used for so many NLP solutions. And there are two types of, if you look into language model, when you're training, you give an input A and it makes a prediction of B, and then reintroduce a B to it, and then it makes prediction C, and then it becomes a little more smarter because now you've given C, and when you input C, it gives an output D. This process goes on until the millions and millions of words you want to train. So this is during training. When you're predicting, you give the first word and say, okay, now create a story for me, a new article for me. It makes a prediction B, and then it just gives that B back into it so that it actually predicts a C, and then goes back into it. So that's what during generation. Language models are used to do so many different things, including language creation. So you actually can create stories. The Shakespearean example I gave you earlier was done using a language model. Yeah.
Would you mind if I announce Keras training class?
Sure.
So I'm one of the organizers for a local meetup, ACM, Association for Computing Machinery. And we have a 2-hour Keras class on Saturday, October 14th. It's part of the data science camp day-long event that is for up to 420 data scientists. So I'll leave some business cards out if you want to look at it later. But what's that?
Oh, what's the format repeating?
What
What's
is?
the cost?
Oh, like $60 for the day.
Yeah, thanks. In machine translation, in this paper, the author said to increase the accuracy of machine translation, where you give an input and then it gives an output, you can increase the accuracy by adding a language model to it. So in a regular neural machine translation or NMT model, based on the encoder's context vector, the decoder will have its own hidden state, and based on the hidden state, it actually starts making predictions on what should be the next word in the translation. But instead of making one word as a prediction, the model can predict what are the top 5 words that should come here. And if you are not sure which is the right word, you can club that with a language model, where the language model looks at what was the words you have predicted till now, and what are the new word, the 5 choices you are giving me. So let's say you have an incomplete sentence and 5 choices what the next word is. So I have 5 sentences, and language model will look at all those 5 sentences and say and tells you which sentence sounds more accurate, more precise, more makes sense, and hence the accuracy of the overall translation goes up using a language model. So actually it's 12:15 now. I know we have to end at 12:30. So I can pause now, and if you guys have any questions, we can talk. There's a lot more stuff I wanted to cover in terms of, let me see if there's anything.
Would you consider covering the episodic memory?
Episodic memory? No, actually I took the slide off.
Okay.
The presentation you have, I think I modified that. That one particular slide I changed. This, maybe you want to read this paper. It's called the Google's Neural Machine Translation System. It's a massive model they trained, just released I think in 2017, Jan, Feb, March sometime, I'm not sure. they have used so many additions in this machine translation. I think the API call, which is available on a public forum in Google, if you go to Google machine learning, I think they use this model in the background so that if you, when you give a sentence in a language and then wants to translate to a different language, I think it's using this model. So it actually has 8 layers of LSTMs, both on the encoder side and the decoder side. They actually have, and the first layer has a bidirectional LSTM. I think I mentioned to you earlier, if you have bidirectional, you have the input sent in one layer in a regular sequence, and there's a second layer in the opposite sequence, so that the words, I think, are closer to each other. They have used residual connections. I explained that concept too, where for every layer, instead of just it depending on the previous layer's inputs, in the residual connections, it also depends on one layer bottom to get the connection, so that the middle layer should not miss out on any information. So that's another residual layer. They have used attention method. They have used low precision arithmetic during inference, where they found if it's a 16-bit or a 32-bit or 64-bit predictions, it takes a lot of mathematical computations, but the accuracy doesn't drop too much if you do lower arithmetic precision, and that's another. Beam search is another concept I did not get a chance to introduce. I wanted to really talk about it. Beam search is the following. Let's say in a translation or even summarization, you have the incomplete sentence and then you have the next word the model is trying to predict. Now, instead of predicting only one word, the top word, which the model thinks is the right word, you can actually ask the model to predict the top 5 words, top n words. And then you have the top n words, let's say n is equal to 3, then you have top 3 words. When you make the next prediction, for each of the 3 words, the next word, it gives a confidence level for the entire vocabulary. So if you have a 10,000 word vocab, for the first word and what would be the next word after that, it picks a confidence level for all the words. So the word after the 3 words, the first word, and word 1 in the vocab, word 2 in the vocab, word 3 in the vocab, word 4 in the vocab, it puts all the words and computes a confidence of this combination. And it repeats for the second word and repeats for the third word. So if the vocab size is 10,000, you actually have 30,000 choices for what would be the combination of the next 2 words for this incomplete sentence. And if you go on, if you keep on doing it, then the numbers are going to be massively high, because 30,000 times 10,000, the next word is going to be. So beam search, what they do is, if you identify the top K is 3 or top 5, or it actually identifies the 3 words, and the next word it will identify of all the 10,000 words, it takes a combination and only takes the top 3 of the combination which has actually highest value, and then it moves on to the next word. So that's a beam search, which actually normalizes the length and also does the coverage penalty. In a sense, coverage penalty is how many words are being covered in the vocab, so that there's an accurate translation happening. They also have a solution for rare words. Let's say if you don't have a word in my training vocab, but in my inference, you're asking me to translate a word which I never saw, then they have a solution, a newer solution. Typically, the solution is, standard solution is, if the model has not seen a word ever and you're asking the model to translate a word now, it actually puts an unk word there, but they actually have found a newer method. It's a good paper, I think, if you guys are interested in reading. And it's 12:20 now. I'll pause, and if you have any questions, I have a few other slides I wanted to talk about. But I guess the 9 months of study, I cannot do it in 3.5 hours, looks like. But if you have any questions, I'll be happy.
How do you get these slides?
Okay, it's here, my GitHub link. Okay, that's my GitHub link, and all the Python files I've used, instructions, plus the presentations, all of there.
If I missed it, did you give any recommendations on toolkit?
No, I did not. For playing, I suggested just play with NLTK as a corpora available, and there's a lot of even they have their own libraries too to play with the text and stuff to understand NLP stuff. But if you want to use a framework to build your models, I think I would say as a beginner you can start using Keras, but really people are using TensorFlow if you want to really do a deeper, more capable files. I think it's good idea to use TensorFlow.
But as to NLTK?
Yeah, NLTK.
Yeah, did you ever word in the market? NLTK is essentially mothballed 4 years ago. It hasn't been active developed at all.
That's true. Yeah.
They could just busy. It was passed out by Spacey though, at least 2 years ago.
Yeah, yeah. Even I think Stanford and NLP also has different corpora, different libraries. Yeah. But this is the for someone to play. If you are a beginner and if you want to play around with some stuff, if you want to have access to lots of corpora and then some frameworks, some libraries to play with it, I think this would actually suffice.
It's great batteries and builder corpora, and the porters down sucks, and a bunch of other things suck. So you've got to mix and match.
Sure.
There's not a single.
There's so many other things too.
Is there any free knowledge base out there since Google retired their knowledge base last year?
There's so much of material available. I think it depends on what you're looking for, whether it's just a translation related. There's so many blogs and papers and corpora available for translation alone. There are free models available, translation models available by different universities.
Not translation, just say part of speech tagging. Where do I learn that Harvey is hurricane or might also be mountain? Where do I learn this?
See, Harvey is a hurricane or not, I think that depends upon what type of data set you already used. And I don't know whether people are updating the data set as such. Stanford actually, I think Greg was mentioning too. Yeah, Stanford NLP actually data set I think is maybe more relevant. But I don't know. I don't do POS tagging anymore. All my NLP research is all in deep networks, so I don't use any of these things myself. So, but I think if you really want to get introduced to NLP and stuff, I think this would be a good study. I'll look at
So you mentioned you're working with the healthcare space, and so I was wondering, like, when you're going through, or first of all, like, what kind of data are you looking at? Is it like claims data, like EMR data, or like are you going through forums from different diseases, or and like what kind of like problems come up in that kind of text?
Yeah. So I'm right now focusing on the cancer research, where I think I'm looking at the narrative part and the image part. We have the scans of tumors, and then also you actually have text of the patient conversation with the doctors. I'm trying to combine these two to see if I can make any sense to define an NLP model to make accurate predictions about what's happening with the patient. Let's say if my question is, will the patient's tumor grow double in the next 2 months or not? If that's a question I want to answer, I think I want to create an NLP model where I actually can look at the scan, look at the data, and then make a prediction. So the multiple questions can be, but my focus area is currently cancer research, and there's a lot of investments happening in cancer research too. Yeah.
Okay.
Yeah, if you want to start a company, that's a good idea also to go into that because VCs can give more money there.
My question was on how would you inculcate both the numerical features and text features if you're doing something, say for the medical applications, say you have the customer reviews or the conditions about the patients, and also you have few statistical reports about the patients as well on the same. How do you combine both of them to create a model? Because combining word to vectors would give you a sparse matrix, and just using a hash maps or something to put both of them together wouldn't give a lot to the model.
Yeah. So you're actually combining multiple things in it, but in the healthcare area, if you have unstructured data and then structured data, so for a lot of companies, what the basic algorithm or approach that they're using is convert the unstructured data to a structured data. So try to do some translation. Mm-hmm. So if the doctor says the calcium content in the blood is low, calcium content is acceptable, calcium content is greater than 10. All of these may be the same thing. So if you have enough rules and using the tagging and all of the extraction and other stuff, and then you identify what the message is and then update your structured data. And then it becomes just a basic database and then you run on it. So, but that's different from the neural networks because they're, right now, half the problem is in the healthcare, especially if using NLP, converting the unstructured to the structured. after you've done the structured data, then you actually can do a deep neural networks to run models on trying to figure out, make some sense out of these data. Now, the word to vec, etc., I have not seen being used as much because the unstructured reports, the narrative reports are being converted into structured report. Because typically the doctor says the patient has high blood pressure. Well, and the next, some other doctor says the patient has blood pressure of 200. If both are same, then let's say high blood pressure may be equal to I don't know, between 120 and 200. So you update that in the record, and then now you actually have all the patient records converted from the unstructured to the structured, and then you run the basic analytics. There it's not deep networks especially. Deep networks comes in NLP is more on the translation, summarization, abstraction. So healthcare is slightly different. Yeah. But if you are using summarization or question answering for documentation available in a tech company, then you can do deep networks to actually do NLP and then get answers for questions or summarization, all of that stuff.
Do you have any recommendation for particularly for finance industry, like NLP?
There's lots of information available online. I don't have it myself, but I've written blogs on pure NLP tech stuff. If you go to my LinkedIn, you can. But my LinkedIn thing is available in the here. Financial, I've not worked on. That's another huge area. I've seen lots of companies working on, especially hedge funds, helping hedge funds to make predictions. But they're not using as much deep networks versus using some of the machine learning models, including XGBoost and some of the SVMs and those things they're using, which is not really deep networks. Yes, sir.
Are POS-based tagging approaches, are they kind of old hat now? Are they becoming obsolete? Because deeper, if you have tons of data, deeper and read it, but if you don't, if you have sparse data, is POS still competitive? Or like ensemble?
The purpose of POS is once you do the tagging of parts, the speech parts in the sentence, you would do a sentence chunking or a segment chunking to identify what are the subjects and the objects and the verbs and negations and those things, and then you actually make a tree, a graph out of it to eventually make sense. I think I gave an example here. The second pronoun resolution. The thieves stole the paintings, they were subsequently sold. Using the POS tagging, you can actually upgrade the text where the thieves stole the paintings, the thieves were the paintings were subsequently sold. So you can update by using POS tagging. One of the objectives is to actually upgrade the text, and then the second sentence, they were subsequently sold, can be written as paintings were subsequently sold. Now this sentence alone will make sense, and you can extract that and you can use that to make your question answering or summarization, whatever it is you're trying to make sense. So for that sense, POS becomes a stepping stone. Healthcare is one segment I think I've seen maximum usage for POS tagging and such tagging, where they're trying to make sense out of the unstructured reports. But once they convert the unstructured into a structured, POS is no more useful. They just do other analytics, basic data analytics, or deep learning.
All the corpus examples are complete grammatically perfect English sentences, but if you look on social media, you've got emojis, you've got hand symbols, you've got like mythology works with their, essentially unstructured text. And any POS tagging is going to be probabilistic, it's not going to be crisp and exact. And nobody's going to pay human raters to sit down 10,000 figures. How do you do with those?
Yeah, so those are all good problems. Actually, like I said, nobody pays. Actually, there are some companies which are hiring third-party companies where they're actually doing human tagging. That's one. I've seen some companies actually creating textual conversions of emojis, and you have multiple tags. Like, say, for example, a textual tags for emojis. They're using that and then replace the emojis and then reconstruct the sentence.
You can do a semi-supervised learning iterative approach. Label some stuff manually, store the remainder.
But yeah, my point is it's not an exact science, it's probabilistic, and the more degraded the text, the more probabilistic it becomes.
Sure.
Especially for people who don't use capitals and shit.
Yeah, that's a problem. Yeah, I don't have a solution for that. Yeah, the people are trying to fire. That's what sentiment analysis. I think even the example I showed and also I talked about later on. Sentiment analysis I think works. I think 95% maybe accurately, or maybe 90%, 100%. I think it's not. People I think are no more talking about just a sentiment analysis for the entire tweet, and they're talking about, okay, instead of just talking about the iPhone, can you tell me which feature you like most and which feature you don't like? Is it the screen and the speed and the look and the feel or whatever? So now becomes an extracting. So people have moved on to
That's an information extraction.
that information. How you could do? Yeah.
So what do the chatbots use for customer service kind of application?
So there's one of the question answering method in the NLP, because you train a model, it actually does language modeling and also does goes and picks up which passage, where the passage is, and what the right answer is for that. So there's multiple things within NLP you use, but I think chatbot is one absolute useful implementation of NLP. Predominantly question answering. Also, if you look at the question answering, that sounds very question answering, but what it means is in the background, it has to know, it has to understand what you're asking, and then identify what where to look for the answer, and then once you know where to look for, then identifying and extracting the answer. So it's a combination of summarization, question answering, sometimes even translation. Chatbots are using for translation also. Okay, thank you guys. Thank you very much.